over DFS, and we're going to start with a recap of BFS, which we covered some earlier in one of our meetings. And both of these are algorithms which can be used to travel through a grid. So BFS stands for breadth first search, and the two algorithms are very similar. Their implementation is just a little different. So with the BFS, it's a breadth first search. It goes level by level. So we start at a point in the grid, and then it expands. Okay, wow, we have 3 more people coming. Okay, hi guys. So we're going over BFS quickly because BFS and DFS are related. If you remember, we went over BFS in an earlier meeting. BFS stands for breadth first search. The way that it works is it's going to travel through the grid starting at a point and it goes out level by level. So that in the first round, we'll go to the squares that are 1 block away from the starting point, and then we'll go out to the squares that are a distance of 2 units away, and so on. So it just keeps expanding outwards like a ripple. And that's the point of this picture in the presentation. The DFS works similarly, except,
Ishan, can you look at chat real quick?
yeah.
Oh wait,
I think
I
I'm
didn't
recording
realize
right
you're
now.
already
Yeah.
doing that.
Yeah. So the DFS works similarly, except we use recursion to explore the grid. So instead of going level by level by adding the squares to the queue, we're going to do recursion. And for those of you who were here for the recursion meeting a few weeks ago, that the reason we covered that is because we wanted to explain how the state space tree works and how recursion works. So recursion is going to go all the way through. Let's say I start over here and the first direction that goes up, it's going to go all the way up. And then it's going to try going up and then to the right and then up. It's going to explore all the directions. And therefore, it's not going to go level by level. We're going to code this and see how it works. So this is going to be really hands-on. You want to like pull something up where you can code. And I'll give you some time to do that. So I'm using IntelliJ. You can, whatever you're comfortable with, you can use. And in your Java class, I'm going to paste this into the chat. That way you don't have to type it out. This is just a pair class because we're going to be doing a DFS through a grid and each square in the grid has a row and column number. We're going to have to use a pair class, not just an integer class for rows or columns. It looks like a lot of people are interested in DFS. Okay. I know the person who just joined wanted me to cover it a while ago, so we're finally going over it. Okay. And we're going to start with a basic example of flood fill, which we covered last time. So you have this character grid of 1s, 2s, 3s, 4s, and 5s. Each of these represents different colors. And our goal is, let's say we choose this square over here. Our goal is to replace all the 3s that are connected to each other with a 6, for example. So these 3s over here get replaced with a 6. So does this, and this one as well, this one as well, and this one. Notice how there are 2 3s over here, but because they're not connected to the main section of 3s, the larger section, they're not going to be changed. And we can solve this problem using a DFS. We'll start at a point and then expand outwards to other points. I'll also copy and paste this into the chat. And after this, we'll start typing stuff together. So the position that we want to change is going to be, it's going to be in row 2 and column 2. So int row equals 2, and I'll say column equals 2. And I recommend you guys code along because it's good to get hands-on experience. And now what we're going to do is we're going to write a recursive function called DFS, and it will take in the row and the column of the square that we want to change. So I'll pass in row and column, and I will also, I'm going to actually make this a static character grid. I'm going to make it a global variable, and I'll just say grid equals new char. There. This way I can refer to it in my function. Now we're going to write our DFS function, and this is going to be a void function that takes in the row and column that we're currently at. So there's just two parameters in this. And now what we're going to do is we're going to get the color of the thing we're currently at. And the color, it's technically a number, but it's whatever. I'll just call it a color. So I'll say char color equals grid row and call. And now that I have the original color, I'm going to go ahead and change grid row and call to 6. So once again, the problem is we have the square over here, it's 3, and we want to change all the squares that are connected to it that have the same color as it to the color 6. And this is kind of like how MS Paint works with the bucket icon where you can change a particular color, a region with a particular color to another color. That's basically what we're coding over here. And these numbers represent colors. Now that we've changed this color to a 6, we're going to have to go through the neighboring squares and change them as well. And if you remember, we could go ahead and do like grid of row plus 1, call, and that stuff. But we also have to check whether that position is inside of the array, whether it's not out of bounds. And let's just go ahead and look at our BFS code from last time. You can see that we had an inside function that told us whether a particular position was inside the grid or not. And the reason for this is because now we're at this 3 over here. We want to check whether we can go up. In this case, we can go up. But let's say we were at this 3 over here. If we try to go to the square on the left, which does not exist, we'd get a runtime exception. So that's why we're going to have to write an inside function. It's going to return a Boolean to us, and it will tell us whether a particular coordinate is inside the grid. How do we do that? We just return whether row is greater than or equal to 0, call is greater than or equal to 0, row is going to be less than 6 because there's 6 rows, and call is going to be less than 6. So this is our inside function. And if at any point you want me to slow down or you need me to paste something in the chat, you can just unmute yourself. And if you have any questions, you can also ask. Now that we have this, I'm also going to create 2 arrays to keep track of how much we should change our row position by and our column position by when we want to go to another square. So if I want to go up, what do I have to do to my row number? If I'm at over here and I want to go to this square, what do I have to do to the row number?
Decrease the row.
Yes, I have to subtract 1. What if I want to go down? Can somebody besides the officers answer? If I want to go down a row, what do I have to do to my current row number? What do I have to add to it?
Add 1.
Yeah, so I have to add 1. If I want to go left, what do I have to do to my row number? If I want to go from this square to this square over here.
You would just keep it as 0 because you
Yep.
wouldn't have to affect the row.
If I want to go left, I keep it the same. If I want to go right, I keep it the same. Now we'll do the array for the column change. If I want to go up, the column doesn't change. If I go down, the column doesn't change. If I go to the left, I have to subtract 1 from my current column number. And if I want to go to the right, I have to add 1 to the current column number. And the whole point of these 2 arrays is instead of manually coding 4 times grid of row plus 1 of call equals 6, grid of row comma call plus 1, all of those directions, these arrays over here maintain the directions that we want to move in. So now all I have to do is just say for int d equals 0, d is less than 4. We're going to go through each of these directions, and our new row is going to be equal to dr of d plus row. Our new column is going to be equal to dc of d plus call. And now that we have these new rows and new columns, there's 2 things that we want to do. We want to check whether this coordinate is inside of the grid, whether it's not lying outside of the grid. Like in this example over here, if we're at this 3 and we try to go to the left, we can't go to the left. There's nothing there. So that's why we're going to check if inside new row and new call. Then we're going to do some stuff. And we also want to check if the color is the same. We don't want to change the color of everything. We have a 4 over here. We don't want to change the color of the 4. We only want to change the colors of neighboring 3s. So we're also going to check whether grid of new row and new call is equal to the original color. And that's why we stored it over here. This is the original color. This color variable is equal to color. And if these conditions are true, Then we want to go to this square over here. We want to go to new row, new call. So now we'll call DFS, new row, and new call. And I just realized there's no reason to have this peer class over here, so I'm just going to delete it. Okay. Are there any questions about this so far? Does everything make sense to everybody? All the steps that we're taking? Okay, let's go ahead and run this and see what happens. I should, okay, wait, can I stop it? Okay, so it just ran. And let's go ahead and print out let's go ahead and print out our array. So I'll just say for char row in grid, I will print out arrays dot to string. Oh, I can't use row. I'll just call it R. Arrays dot to string R. And let's see what happens. And look at that. It's basically replaced this patch of 3s over here that were connected to each other with 6s. It's replaced all of them with 6s. And you can also see that this small patch of 3s over here in the bottom left corner, it stayed the same. It hasn't changed because it's not connected to the bigger patch of 3s. Are there any questions about this? Okay, I'll paste the code into the chat if it fits. It may be too large, but if it's too, yeah, it's too large. I'll just put it on GitHub. Okay, this is a basic example of DFS using Floodfill, and you can go ahead and play around with this for a bit. The second thing that we're going to do is island counting. So I'll go ahead and create a new class, and you can create a new class as well. How do you check the number of 3s side by side? Are you asking how would I check the number of 3s? Like if I wanted to count how many 3s were in this region that just changed, how would we do that? Because right now we did not count how many 3s were changed. If you wanted to count how many 3s were changed, you could have a counter variable. And then over here, you would say counter plus plus in your DFS function. And then we can say over here, we'll print out changed counter 3s. So now when I run this, it will print out change the 9 3s because it changed these 3s over here, these 2, so that's a total of 6, and then 7, 8, 9. So that's how you find out how many positions were changed. Okay, let's go ahead to the island counting example. And I'm going to go ahead and copy some of the code from my DFS class, in particular the grid, because I don't want it to retype everything. So static char grid. And in this example, we basically have a map. And the pound symbol in the map represents land. Periods represent the sea, the ocean. And there are some areas of land that are connected to each other, like in the top left corner. And there are other areas that are separate. I should have prepared this beforehand. Okay, so in this example, we can take a look at this and just easily see that there's 3 islands. But how would we write code to count how many islands there are? Oh, is this a lead code problem? I didn't know that.
Yeah, it's a lead code problem.
Oh, that's so cool. Okay. Yeah, this is pretty much exactly what we're going over. So we'll code it together, and then you guys, if you have a leak code account, you can go ahead and submit it there to see how fast it runs and other things like that. But how would we write a program that would count how many islands there are and also print out the size of each of these islands? Are there any ideas? Does anyone have any ideas for how we could do that?
I do.
No, okay, not the officers. I'll give you a clue. The answer consists of 3 letters. It rhymes
Maybe
with,
use maybe use DFS to search through each of these through the space and find out which ones have pounds nearby.
yeah, that's correct. We'll use a DFS because that's what we've been covering so far in this meeting. Okay. And the logic behind this is because there are multiple islands, we may have to do multiple DFSs. So for example, we'll do a DFS in this square and then we'll go to these regions over here. But because this island over here and this island over here, they're not connected to the first one that we found, we're going to have to do multiple DFSs. So the way that this will work is we'll have a for loop, and I'll say int n equals grid.length. This is just how long my array is. And this is not a square array, okay. Okay, so we're going to go through each of these positions. We'll use a double for loop. And what we want to do is if this position is a pound symbol, so if it's land, then we want to do a DFS. We want to do a DFS here. So because it's a pound symbol, it's land. And then we'll write DFS, and then we'll pass in our current location. And then there are a couple of things I want to do in this problem. I want to count how many islands we have. So we'll have a variable over here, int islands equals 0. And I also want to print out the size of each island. So I'll say static int size. And each time I do a DFS, I'm going to reset the size to 0 because I want to set it to 0. Then I do my DFS and then I'll print out the size. So then I'll say this island has a size of, and then the size. And you can see this is in red because we haven't written our DFS function yet. So let's go ahead and do that. Are there any questions about the logic so far though? The fact that we have to do multiple DFSs because we only want to go to a square if it's a land symbol, but because not all of the land symbols are connected to each other, we're going to have to use a for loop to go through each of the positions.
Would we need to make like a visited array so that we don't go we don't cover the same island 2 times?
Yes, that is correct. We would have to use a visited array.
Or there's another way we could do it.
Or you could change the, go ahead.
Yeah, you were saying it. Like we could just change.
Yeah.
We could mark the islands as water as we visit them.
Yeah. So if you remember in this example over here, with the BFS, we had to have a visited array as well to make sure that we're not going to the same square over and over again. You can see here we had a visited array. With the DFS, for the flood fill example, the reason we didn't need a visited array is because as we went to squares, we changed them, so it was fine. With the island counting, we don't want to keep repeating the squares because we're not going to be changing them. If something's land, we're just going to leave the square the same. So that's why we're going to have a visited array as well. And what this visited array tells us is whether or not we've already been to a particular location. That way we don't get caught in an infinite loop and keep repeating. And our DFS function will take in the row and column number, as mentioned earlier. And inside of our main function, we'll say visited equals new Boolean. It's going to be grid.length and then grid of 0.length. Okay. And now the logic is really similar to how it was before. I'm going to copy over some stuff now, like the DRDC arrays. We already know how that works, and no need to type that out again. Also copy the inside function. That way we don't have to retype everything. Okay, and now the logic is if we're at this, in our DFS function, if we're at row and column, we're here because it's a land square. It's like a pound symbol. So that's why we're going to increase size by 1. And remember, size is the size of our current island. Now what we're going to do is just as we did before, we're going to go through each of the positions, up, down, left, right, up, down, left, right, yeah. And we're going to say new row is going to be equal to dr of d plus row. and new call is equal to DC of D plus call. And this represents a possible square that we could go to. And just as we did before, the first thing we have to do is check whether this position is inside of our array. So if inside new row, new call. And I also realized that there are 6 rows and 5 columns. So this should be call is less than 5 over here. If it's inside, and what's the second thing we had to check? So we're considering going to this square over here located at new row, new call. The first thing we did was check whether it's inside the bounds, because obviously we don't want to go somewhere if it doesn't exist. What's the second thing we have to do? What's the second
Check
thing
if
we have to
it's
check?
already visited.
Okay, already visited. We could go ahead and do that. And in our DFS function, when we go to a row and column, we're going to set it as visited because we don't want to go to it again. So outside of our for loop, we'll write visited row of call equals true. And now, as Shrey said, inside of our if statement, if the new square we're going to is inside the grid and it is not visited, then we're going to go to it. And there's a third condition. What's the third thing? Like, do we want to go to any square or do we want to only go to particular squares?
If it's a hash, then only go to it.
Yeah, the whole point of this problem is that we want to count the size of each of these islands and how many islands there are. So we only want to go to a position if grid of new row and new call is equal to a pound symbol. And I just realized this should be new row and that should be new call. So the third condition will be that grid of new row and new call is equal to the pound symbol. That the new place we're going to is land, because if it's C, we don't want to go to periods. We only want to go there if it's a pound symbol. Is everybody following along? I just want to make sure that everybody understands this. Okay. So if this is a valid position to go to, then we're going to call DFS new row and new column. And before we run this and just test if it works, outside of our for loop in the main function, so once we've gone through all of the squares, we're going to print out the number of islands. Just say there are, and then plus islands. And over here, every time we do a DFS, that means we found a new island. So we're going to increase the number of islands by 1. And now we'll run this and we'll see what happens. Okay, so let's take a look. It said this island has a size of 7. This island has a size of 1, 2, 1, 1, 1, blah, blah, blah. And it says there are 12 islands. But is that correct? Are there 12 islands over here?
No, there are 12 pound symbols.
Yeah, there are 12 pound symbols, but not 12 islands. There's only 3 islands. So over here, in addition, when we're doing our DFS, we not only have to check whether it's a pound symbol, but we also have to check whether or not it's been visited. Because let's look at this example over here. Our I and J started out at 0. So we start our DFS at this square, and then we mark this as visited, this as visited, this, and this as visited. And that's one island that has a size of 7. Okay, so that part is good so far. And then J becomes 1. So then we go to this position over here. And the thing is, it is a pound symbol, so it technically is part of an island, but we've already counted the island that it's part of. We've already visited it. So that's why over here, we want to do a DFS if it's land and it's not visited. So let's check over here. If grid of I of j is equal to the pound symbol and it's not visited, then we go ahead and do our DFS and other things. So if we run this now, you can see here it prints out there are 3 islands. This island has a size of 7. That one has a size of 7. This island has a size of 2. And this island has a size of 3. And that's the solution to this problem. So you can pretty much, if you were following along, you could copy and paste it into the lead code problem that Kanishk gave us. And you can tweak it a bit to read in the input, and then, well, actually they read in the input for you. So you can go ahead and submit it. And you can play around with this a bit more. Are there any questions about how this works over here? Any questions at all? Cool. Let's go ahead to Google Docs. There's a document posted on Google Classroom called List of All Problems. It hasn't been updated in a while, as you can see, but it has some really good problems on there, like binary search and BFS problems. Yeah, these are BFS problems. I think coast length can be solved with a BFS or a DFS. Let's go ahead and take a look at them and discuss how we would solve them. Okay, so here's the grid problem. I'll basically summarize it for you. So you're basically given a grid of numbers, and the number of a particular square tells you how far you can jump in any direction. And you start at the top left corner. Your goal is to get to the bottom right corner. So in the first square, you can make a jump of size 2. You can jump there, then you can jump here, and you can keep on jumping. And this is just an example that they gave over here. There may be multiple different paths to get to the bottom right square. And in this problem, you need to print out the minimum number of steps to get to the you need to print out the minimum number of steps to get from the top left corner to the bottom right corner. Does anybody have any ideas for how they would code this or implement it? What approach would you take?
So you could do the same process with with our DFS algorithm, but for like calculating the jumps, make it so that the number inside the square is multiplied by the item in the DR and DS.
Yep, that's exactly correct. So what Shreya said is we can basically do our regular DFS that we have coded up over here. We start our DFS over here, and we're going to go to all the visiting squares. But what we were doing over here is we're increasing it by 1 or decreasing it by 1. Instead, what we want to do is, because this number in the grid tells us how far we have to go, DR and DC basically tell us the direction. So instead of just going by 1 each time, we're going to multiply it by, let's pretend grid is the grid that they gave us an input. We're going to multiply it by grid of row and call. So for example, if we start in this top square, which has a number 2 in its position, instead of moving one spot to the right, we're going to move 2 times 1 spot to the right. So 2 times 1 is 2. We're going to move to this position over here. And if we want to move down, instead of increasing the row number by 1, so instead of increasing this by 1, as we have over here, we're going to multiply it by 2 and then move down. Yeah, so that's correct. That's how you would do this problem. That's how you would do it. It may require a slight modification because they want the minimum number of moves. I think you may have to use a priority queue. But yeah, doing a DFS will definitely give you the number of steps you can take on any path to go from here to here. It just may not be the smallest. Because unlike a BFS, a DFS goes all the way out as far as it can, and it may not always be the optimal way. So for shortest path problems, it typically has to do with a BFS. But yes, that's the right logic. You pretty much reuse the same code that we have here for the BFS. And just like Shreya said, you would multiply by whatever the position is in the grid. So that's the solution to this grid problem. Are there any questions about it? Next one is coast length. You guys can take a look at that, but I'll just stay on this tab if there are any questions. It doesn't look like there are any questions. So let's go to the coast length problem. So this problem is kind of similar to the island counting ones that we've been doing. And I'll give you some time to read it. It's a little lengthy, but maybe you can just read the part underneath task. Are there any ideas for how you could attempt this problem? It's kind of similar to what we did.
My first thought is maybe to, if like any non-land square is surrounded by land, then convert it to a land square.
Okay.
Because of that one little spot on the example.
Uh-huh. Okay, so for this problem, yeah, you would again have to do a DFS, and what you would do is, I actually forgot how I solved this. It's been a while. Oh, I'm not logged in. Yeah, whatever. Okay, so yeah, it's kind of like what Kanishk said. You would have to do a DFS, and you would, for each of these squares, that's a land square, you would look at the square surrounding it and check if it's the ocean. And then you would increase your count for the coast length by 1. And for those who didn't read the problem or didn't fully understand it, you basically have these islands over here, and you need to count the length of the coast, and that's shown in the bold black lines over there. So yeah, you would, for each of these land squares, which is represented by 1, you look at the surrounding squares, and if it's a 0, you increase your answer by 1. However, you may notice that you can see over here, there's a little lake in the middle of this island, and that does not count as part of the coast. So I forgot the exact method. I forgot how you're supposed to tell whether a certain square is inside the land or not.
Would it work if you also did a DFS for every 0 square, checking to see if it's surrounded by all land tiles?
Yeah, that could work. You can do so basically, instead of doing the DFS for ones, you do a DFS for zeros, and then you check whether those zeros are surrounded by ones or not. Yeah, I'll come back to this question if there are any doubts about it or anybody has any more questions. And then there's this problem. It's a really nice problem. So this will be the last one we discuss for today. I'm going to go ahead and log into Kattis. But take a look at that fire problem. Okay, I remember how I did it now, looking at the code for. So my code's in C++, but I'll explain the logic anyways. What you would have to do is, like Shrey said, for each of these zeros, what you're going to have to do is you're going to do a DFS, and you're going to mark all the water that belongs to the ocean. So this 0 over here is part of the ocean water. So is this 0. and this 0 as well, and this 0, and you keep doing the DFS and they all get marked as ocean water. But you can see that this 0 over here is not in the center. It is in the center. It is in the center, so it's going to be marked as, it's not going to be marked as ocean water. And that's the logic for that problem. And now for the fire problem, where's that? Let me just open it. So this fire problem is pretty good. I hope you guys got the chance to read it. And if not, basically you have you have John over here, and he's in a maze, and he's trying to get to the outside of the maze, so that the borders of the maze, and the F represents a fire. And at each second, the fire expands outwards by 1 step, and John can also go 1 step each second. He cannot go on squares where the fire has been. So for example, he cannot go to this square on the right because that's where the fire is. And he cannot go to this point over here and then come back to where he was, because 2 seconds later, the fire would have already been on that location. So the fire is spreading, and his goal is to get out of the room before the fire prevents him from escaping. And if he can escape, you have to print the shortest amount of time it takes for him to escape. Otherwise, you have to print whether it's impossible or not. You have to print that it's impossible. So in this example, we have the fire in the corner. In the first second, the fire is going to go to these 2 squares and these 2 positions. And it happens that those are the only 2 positions where John can move. And because of that, he's going to not be able to escape. And that's why the answer is impossible. So this one's trickier. And I'll give you some time to think about it. I think one of you in the meeting has solved it before. I'm not sure. But if anybody has any ideas or want to share some observations that they made, you can go ahead and do that. Oh, I think the person who solved it has left. It's not here anymore. Okay, so this problem is a bit trickier. And the idea is, if you remember back when we covered the BFS, we didn't do just the flood flow. We also did the BFS to find the shortest distance to each of the squares. I think it's called Bfs Maze. So let's go ahead and run Bfs Maze and take a look at what it does. This code over here is also on GitHub. And basically we start at this position. Where do we start? We start at position 2, 4, I think. Well, anyways, we start at some position in this grid over here. And what it does is it outputs the shortest distance to any square that is an empty space. So the @ symbol represents walls, and it'll print the shortest distance. I think we started over here. So that's where we start. And you can see the shortest distance to the square on its left is 1, and then 2 and 3. And you can see how it changes as the distance from the source increases. So this BFS code finds the shortest distance. And for this problem, we can apply that logic over here, because what we'll do is for every single square that is not a wall, we'll find the shortest amount of time it takes for any fire to reach it. So in this problem, there may be multiple fires. In the test cases that they gave, there's only 1 fire in each test case, but they can be like 10, 20, 30 fires. So what we want to know is the shortest amount of time it takes for a fire to reach a square. And for that, we'll add all of our fires to a queue, and then we'll do a BFS just like we did over here. And we'll find the shortest distance to each of these positions. Now that we know the shortest amount of time it takes any fire to reach a square, we're going to do a BFS for John. And in this BFS for John, we can only move to a square if it's a period. So if it's not a wall, it has to be a period. And the amount of time it takes John to reach that square is less than the amount of time it takes the closest fire to reach that square. So that's how you would solve this problem. You need 2 BFSs. One BFS, you would add all the fires into your queue and do the BFS to find the shortest distance. The second BFS would be to determine whether you can get out and how quickly you can get out. And if you find that your queue is empty and you haven't reached one of the border squares because the fire has blocked you, then you print impossible. Otherwise, if you find yourself on the border, you would just print out however many steps you had to take to get there. Because remember, the BFS works level by level. So the first time that you get to a border square will be the shortest distance it takes to exit the maze. And that's the solution for the fire problem. It's a really nice problem. Yeah, and that pretty much concludes today's meeting.
Someone to get her. Just a progesterone test.
Are there any questions about DFS or BFS at all? Next week, we'll be covering a data structure called a binary search tree. I don't know, I think it's covered in Computer Science 3, and it's a nice, important data structure. So that's what we're going to be doing next week. And either the week after or on May 3rd, we still have to decide, we'll be doing APCSA review. We'll be reviewing for the APCSA exam in Computer Science Club. So if you or anybody you know is taking AP Computer Science A and you would like to have some free tutorials where you can review, we'll be covering the content in those meetings and we'll let you know when. You can just let your friends know. And that's about it for today's meeting. You can stay if you have questions. Otherwise, thank you for coming and bye.